Hi everyone, and welcome to our webinar on modelling railway bridges using LimitState Ring. My name's Tom Pritchard, and in a minute I'll be introducing you to our speaker for today, who is Matthew Gilbert. In today's webinar we'll be discussing how you can model railway loading and common railway bridge features using LimitState Ring, as well as outlining why modelling true-to-life railway loading vehicles and actual configurations is important. This will be interspersed with some practical examples which will use the software. The presentation itself will run for about 40 minutes, and we're going to include a few minutes at the end for any questions that you might have. These can be posted at any time via the question box that should be present in your webinar interface. We do try to endeavour to get through as many of your questions as we can in the time available, but for obvious reasons this isn't always possible. We do, however, make sure to respond to all unanswered questions via email after the webinar has finished. For anyone who does have questions regarding the software that require a long answer, or if you just think of something after the webinar is finished, then please feel free to contact us outside of that webinar time, and we will be happy to answer these in detail for you, and I'll give you our contact details at the end. So without further delay, I'd like to introduce you to our speaker for today, who is Professor Matthew Gilbert, and he's the product manager for LimitState Ring.
Thanks very much, Tom, and thanks very much everyone for joining us today for the webinar. Okay, so the first slide gives us gives you an indication of the types of bridges that we might be assessing using LimitState Ring. Two railway bridges with two different loading regimes. The first one is a nice simple voussoir free-span bridge. The second one has more complex construction. It's a multi-ring brickwork arch bridge. But both types of bridges can be assessed using the software. So just give you a quick lowdown on what we're going to be covering today. First of all, I'll say a few words about LimitState, the company that develops the software, a bit of background to the topic, and then focusing on railway loading and application of the software to railway bridges before wrapping up with conclusions and then opportunity for you to ask questions. So first of all, just a few words about LimitState. Actually been around now for probably around 12 years now. Spun out from the University of Sheffield, and the aim of the company is to provide engineers with powerful analysis and design software, focusing primarily on ultimate limit state analysis, although not exclusively. And what we do is we use methods not commonly used by other analysis tools in order to very quickly provide useful solutions to the engineer, and also make sure the software is well validated and easy to use. And we have many companies, large and small, using the software. I think about 30 countries worldwide. Where does our software fit in? It really sort of tries to bridge the gap between traditional sort of hand-type calculation methods and advanced nonlinear finite element, discrete element type approaches. And the idea is to try to get the best of both. So we have an easy-to-use user interface, rapid solutions. On the one hand, so that's in common with traditional tools, but on the other hand, we can actually take account of localized material properties, for example, in the same way as you can with the advanced tools. The main benefit being that we can get solutions much more rapidly. Background to the webinar: if you think of railway bridges, in the UK alone, there are over 25,000 bridge spans carrying railway loading. The situation is similar in many countries in Europe, and for that matter in many countries around the world. Most of these bridges are well over 100 years old, often carrying heavy loads and require regular assessment. The other thing to say is very often they contain unique details, which is very useful to get a handle on in the analysis. So as we'll see, LimitState Ring allows us to model details, so we can do that. Okay, what is LimitState Ring? It's an interactive software tool for investigating the stability of masonry arch bridges. We can use the software to model both single and multi-span bridges, a wide range of potential failure modes, localized properties as I mentioned. We can model the effects of vertical live loading from vehicles, or we can also use the software to model the effects of support movements, and those could be vertical, horizontal or rotational in nature. And also a slight slightly esoteric feature, I guess, is we can actually put in reinforcement into the analysis as well. Personally, I have mixed feelings about putting in reinforcement. I think if you're going to upgrade your bridge, there are normally more effective ways of going about that. But you may inherit a bridge which has reinforcement, and you can take account of that in the analysis as well. What I'll probably do before I get on to how the software works is actually just start up the software, just to show you how you can get a bridge set up and hopefully get a solution pretty quickly. So when you start the software, you have effectively a kind of wizard, new bridge wizard, and what we will do is we'll use that wizard to set up, in this case, a railway underlying bridge. So that's a bridge carrying railway loading. Initially, on the first pane of the first dialogue of the wizard, we're asked various details about the bridge, which I'll skip. We're also asked about what the effective width of the bridge is. So essentially, LimitState Ring is a two-dimensional program. So what we have to do is make some assumptions about the width of bridge, which is going to be actively carrying whatever the prescribed applied loads are. And we can do various things. We can fix the bridge width, or we can actually have automatic bridge width based on some assumption of transverse distribution through the backfill and bridge. So if I'll keep that as an automatic bridge width for now. Then move on to specify the geometry. So first, well, we can actually specify details of the abutment, but very often we move straight on to describe the span on the assumption that the abutments are sound and providing an effectively rigid support to the arch barrel. If we do that, you'll see there's various different options about the type of masonry structure that we're dealing with. Have we got a stone voussoir arch barrel, a bonded brick, multi-ring? And also, we can choose the shape of the structure. What I would recommend that you do wherever possible is use one of the user-defined profiles in order to get a good representation of the arch barrel in your analysis. However, for the purposes of this quick run through, I'll keep as a segmental shape, because that means I don't need very many inputs. All I need is the span, the mid-span rise, and the ring thickness. And if I've just got a single span, then that's really all I need to do in terms of the geometry. Move on to the fill profile, which I'll keep as a default. Obviously, in reality, you would take account of the real fill profile. And what you can see is actually behind the wizard is that it's busily building up the geometry of the structure as we speak. We've then got partial factors. For the purposes of this analysis, I'll keep these as unity, but in the next example, we'll actually put in some non-zero parameters from an assessment code. Move on to the masonry. We can choose to have all the masonry the same, or we can choose, if we had a multi-span bridge, for example, we can choose the piers to be different masonry to the barrels, for example. Here I'll keep everything the same. You can see that the key parameters that we're looking for are the unit weight and the compressive strength and the angle of friction. Moving on, backfill we can describe, and describe that in terms of unit weight, angle of friction, cohesion, and then in terms of the anticipated effects of the soil, modelling dispersion of live load, modelling horizontal passive restraint. And then we finally come to a railway specific entry here. We're asked to provide details of the track and ballast. So again, we can enter some details of that, the unit weight and the angle of dispersion in this case, and then also some details of the track. So what is the track load per unit area, what's the spacing between sleepers, what's the sleeper length, breadth, height, etc. And some of these indicated are for display purposes only, so the sleeper height, for example. And then we move on to the loads. So we can basically choose from a range of inbuilt vehicles in the vehicle database. So here we've got some UIC vehicles, some UK railway load vehicles, Network Rail, Indian Railways, and user-defined in this particular case. So actually I'll come to those user-defined vehicles in the next example. For this one, I will, for example, choose a Network Rail loading. You can see actually here we've got various different options. We've got basically a single BSU load pattern and then a more normal 20 BSU load pattern, 20 British Standard Units. But for people who are not familiar with this, it's really just giving you a series of axle loads and spacings. And because we've got a single span bridge, I'll actually choose here the short length option, and I'll put that into my bridge. And so then I end up with, you can see a series of 2 axle loading on the bridge, and you can see that as soon as I move the vehicle, I end up getting automatically the deformed response of the structure. The other thing you can see in the console is I've got something called an adequacy factor. So in the console output, it's telling me here that the adequacy factor is around 4 with the vehicle at that position. If I move it slightly to the left, it gets bigger. If I move it slightly to the right, it gets slightly lower. It goes down as far as 3.87, 3.88. So it's actually around 3.9 looks to be the lowest one in this particular case. Now bear in mind I didn't apply any partial factors. If I'd applied partial factors to the axle loads, then obviously the number that I get in terms of the adequacy factor would reduce. So basically, if you apply those partial factors to the axle, you're expecting then the adequacy factor to be at least 1 in order to have a safe structure. So what you can see hopefully is that very, very quickly you can build up a model. One of the things I did earlier was have an effective width which was automatically calculated. So if I move the load, you can actually probably just about see that as I move the load away from the mid-span, that the actual thickness or width of the bridge being assessed actually changes. And so the reason for that is that it's common in assessment codes to have an effective width which is based on the distance from the applied load to the point at which it touches the arch. So when I'm applying the load just above the abutment, that distance is greater, hence the calculated effective width is greater. Okay, but I think that's probably gives you hopefully a little indication as to how the software works. I'll go to how it actually works in terms of conceptual basis and how it actually works in terms of mathematics now. So really what we do is we split this masonry arch in the bridge into blocks. We assume those are actually rigid, separated by contacts. And we say that of all the permissible equilibrium states, that's lines of thrust fitting within the arch geometry, and there are multiple permissible equilibrium states because we have a statically indeterminate structure. But of all those permissible states, we use optimization to find the one corresponding to the maximum load factor. And that also corresponds to the point at which we get a mechanism of failure. And that mechanism of failure could involve 4 hinges, as in the example shown here, or with different material properties, maybe it might involve sliding failure, as shown in the slide on screen right now. So the method is general. It will look at the properties and it will use rigorous mathematical methods to find the critical load factor for your particular set of inputs. What we can say if we step back is that this is the shape of the arch in relation to the pattern of loading which governs stability. We also, in addition to the arch barrel, we have surrounding fill material that also helps provide additional reserves of strength. What it basically does is provide pre-stress from the self-weight. It provides distribution for whatever live load you apply to the fill, and also it provides passive restraint as the arch barrel wants to sway into the fill material. The other thing to say is that modern methods of analysis tend to focus on the ultimate limit state, and they assume that the serviceability limit state is implicitly satisfied. That's something that's the subject of active research, and hopefully we will be able to have a slightly more refined approach to dealing with this in the near future. In terms of the mathematics, if we're thinking about the ultimate limit state, what we're doing is we're maximizing the load or load factor lambda in this case, subject to equilibrium and yield. And if we think about equilibrium, don't need to worry too much about the equations. We can just say that for each given block in the structure, it must be in equilibrium in the y direction, the x direction, and in the rotational sense. So what are the forces applying on that applied to that block? Well, there's obviously the self-weight of the block, but there are also forces from the contacts, in this case, at the top and bottom of this block in the pier. So we satisfy equilibrium. That's the first set of constraints. And then secondly, we have inequality constraints, which are there to ensure that yield is satisfied. And yield could mean sliding failure. So for sliding failure, we make sure that the shear force doesn't exceed the coefficient of friction times the normal force in terms of magnitude. Similarly, if we want rocking failure, in this case assuming that we have infinite compressive strength for simplicity, then there's a relationship between the magnitude of the applied moment we can apply and the magnitude of the normal force and the thickness of the contact. But the main thing is this boils down to a linear optimization problem, which is nice and easy to solve. How does that manifest itself in the software? Well, it means that we can calculate the location of the hinges and the thrust line. If we relax one of the assumptions and say that instead of having infinitely strong in compression blocks, we have a finite compressive strength, and we have a rectangular crush block in our idealization, then we end up, instead of having a thrust line, we have a thrust zone, and that can be plotted graphically as shown here on screen. In terms of the loads, we're distributing these loads through the fill material, and we'll come to that shortly. There's something else here, that the backfill and backing areas in the software are modelled with one-dimensional elements, and basically those elements can carry a prescribed amount of force in compression. If there are backfill elements, then that is a function of the angle of friction of the soil. If it's a backing element, then the user can enter what the assumed compressive strength of the backing is. But they carry a force in compression, and for sake of simplicity, they carry zero force in tension. So that's equivalent to saying that active soil pressures are so negligible as to be ignored in the analysis. So that sums up the main elements. In terms of the loading, then that's a clear differentiator between highway and railway bridges. And the software incorporates a standard model for distribution of load through the track. And also the software includes, as we've briefly seen, a range of standard railway loading vehicles. In terms of distribution through the track, the standard model is to take the load from an axle, for example F1, and assume that half of it is distributed directly to the sleeper directly underneath that axle, and then a quarter of the load is transmitted through each adjacent sleeper. So we have this quarter, half, quarter model. In terms of the dispersion below sleeper depth, then effectively the user is free to decide what those angles of dispersion are. There are inbuilt defaults in the software that date back to the time that this software was developed in association with International Union of Railways, but you can change those to suit your assessment code, or if you have particular knowledge about the types of material you're dealing with. So here you can see again, you've got a concentration of load directly into the axle, and then reduced loading either side of the axle. In terms of transverse distribution, then a similar thing applies. If you want, you can distribute from the end of the sleepers, or effectively you can set the sleeper width to be the same width as the axle width, in which case you're effectively saying that the sleeper doesn't provide significant distribution beyond the wheelbase. So you then end up with a transverse effective width that you can use in your assessment. Now you've got to be careful with that effective width. You may have quite a significant effective width. You then go and look at your bridge and you find that you have longitudinal cracks at particular spacing, and clearly you're not going to get significant distribution beyond those cracks. It makes sense then to use a custom effective width, which is set as the distance between those cracks. Similarly, if you have close proximity of the track to the edge of the bridge, then you need to set some sort of cutoff on that effective width so that you don't have an overly generous width in your calculations. In terms of railway loading, there are built-in models from UIC and the Eurocode. So for example, load model 71 is 4 250 kilonewton axles. You then have UDLs in the approaches to those axles. Generally speaking, for masonry arch bridges, that kind of UDL, uniformly distributed load, is beneficial. So by default, those are not included in the inbuilt models. Similarly, network rail vehicles are included in the software. Again, the UDL that's associated with the standard RA1 load model is not included. And there you can see how that RA1 loading looks in the software. You can see that actually it's got quite a number of axles at particular spacings. Now, what you can do if you have particular needs is you can create your own vehicle, and you can actually save that vehicle as a custom vehicle, so that when you're next assessing a bridge, for example, on the same stretch of railway line, you can use that custom vehicle again. And here we can see how complicated actually, or how many pressures are superposed when you have these quite complicated arrangements of axles, such as RA1 axle loading. So you can see that each of those axles is split into effectively 3 discrete loadings, which are then distributed down onto the bridge. We've talked about the track and ballast properties. What we haven't talked about explicitly is the partial factors on the loading. Now, what you can do is you can apply a load partial factor to the axles, but also you can choose to have a separate dynamic factor, which is selectively applied to one or more of the axles in your vehicle. And if you select that dynamic factor, you can then choose to apply that to one or more axles in your vehicle, as you can see on the right hand part of the screen. Other loading effects, vertical effects you can model. So for example, the vertical effects of nosing, centrifugal effects. Horizontal forces are currently not easy to model. There hasn't been very much, to my knowledge, in the way of testing of horizontal forces for masonry arch bridges. So at the moment, there remains something of an unknown, and hence there's not a direct way of modelling those in the software. Application of the software to railway bridges. I've got a nice example here of a multi-span viaduct which is subjected to freight loading. Actually, this is based on the type of loading which was applied to a whole number of bridges in the northwest of England and the southwest of Scotland some years ago. What the operator did was change the types of wagons that were used, so that instead of having quite short wheelbase wagons, for economic reasons it was more cost effective for them to use heavier, longer wheelbase wagons. So what we're going to do is look at the effect this might have on a representative bridge of this type. What was observed following the change of that freight loading was quite serious and widespread signs of distress. So the axle loadings did increase, but it was pretty marginal. It was less than 10%. What is more significant, we think, is the change of the pattern of loading. And in terms of symptoms, the symptoms, for example, cracking between the arch barrel and the spandrel walls, loose masonry, so lots of warning signs that actually something is amiss, and that change of pattern of loading is effectively having an adverse effect on the lifespan of these structures. These are the two types of wagon that we used. Short wheelbase wagons, HAA, and the longer wheelbase wagons, HTA. And question is, could it have been predicted that the change in wagon type would cause problems? And I would say yes, and we'll see if that's the case if we actually put in the representative dimensions of the of one of those bridges. We can see quite clearly the effect of that on the outcome. So what I'll do is I'll just go back to my new bridge wizard. For speed, I'll have an effective width that's built in of 2.5 meters. I'll go straight onto the span. I'll put in, rather than a user-defined span, I'll put in an indicative set of dimensions for the types of bridges that were found to be affected by this change. So 50 meter span, roughly 7.5 meter rise, so roughly semicircular, and 900 millimeter barrel thickness. It's a multi-span. I'll model 2 spans. The height of the pier, I'll say it's 12 meters, 2.3 meters pier thickness at the top, and 2.4 meters at the bottom. Move through. The second span is automatically the same as the first unless you specify otherwise. Full profile, it's of the order of 8.4 meters above the pier. I'll put in those partial factors that were shown on the overhead. So 1.9 for the axle load and 1.8 for the dynamic factor. I'll keep all the others the same. I'll keep the defaults for all the other properties that we've seen. But for the vehicle database, I've actually got a HA wagon and a HTA wagon already built in. And I will use that in my analysis. So if I click finish, we've got this short wheelbase wagon there to actually use. And what I can do is I can move this across the bridge and I can see where the critical loading point is. I can do this by hand manually, as I'm doing now, or certainly shown in other webinars, you can see you can actually automatically run this across the bridge if you prefer. But in terms of the load factor, it's looking like the minimum load factor is around 2.1, something of that order. Yeah, so something like 2.1 is the critical. You can also see that the software is automatically picking up this multi-span failure mechanism. If I apply the load there, if I apply the load at a different place, it will automatically find a single span failure mechanism. So the general nature of the calculations means there's no need to specify whether you're looking for a single or multi-span collapse mechanism. It will work that out for you automatically. Okay, so 2.1. If I go now and just change the vehicle. So change that to a HTA wagon. So import that into my project and see what effect that has. You can see now instantly that we've got this very different distribution of axles effectively. If I click solve now, then actually instantly I come down from 2.1 to 1.3. So although I had only an 8% change in axle load, I've got a much bigger than 8% difference in adequacy factor. So we can see very, very quickly that this particular distribution of axles is likely to be much more onerous as far as this bridge is concerned than the previous one. The other thing I haven't done is actually, I haven't actually in either of these runs actually select where my dynamic factor is applied. If I do that, then apply it probably around axle 5 is probably as good a place as any, and solve again. Then actually, so now and what you can probably just see which one has got the biggest. Which is the axle 5? Let's just see it. That's axle 4. So this is axle 5 here. Oh, it's this one. This is that. No, it's that one. That's axle 5. So you can try different positions of the dynamic factor to find which is the most onerous. It's actually measured from the left. I'd forgotten that. So it's 1, 2, 3, 4, 5. Is that right? Anyway, sorry. It starts at 0. Yeah, it starts at 0. 1, 2, 3, 4, 5. The main thing is that we've now got an adequacy factor which is below 1. So what that's telling us is that this bridge is likely to not have sufficient reserves of strength to carry this particular type of traffic. The other thing that I probably haven't got time to talk about, but there are other webinars where it's covered in more detail, is just to very briefly note that it is possible to specify local properties. So for example, if we had mortar loss in the structure, for example at the base of the pier, for example if this bridge is over a river, you might have got mortar washout, we can see what how that affects the adequacy factor. It's actually taking it down from 0.976 down to 0.947-ish. So you can play around applying local properties to see what influence that has on the structure. Okay, so we go back to the presentation and just wrap up with some conclusions. In terms of railway arch bridges, LimitState ring allows railway loading to be modelled, including track ballast and the load spreading effects. Allows single and multi-span bridges to be modelled, and it allows defects in bridges found in the field to be modelled directly. So for example, in that last case, mortar washout, you could model that. What I would also say is you could also specify that is put right through some routine maintenance as another option. So that concludes my presentation proper. I've just got a few minutes to pick up questions, so I'm just going to have a look at the dialogue now and see how many questions that we have. Okay, I'm just looking at one. How do you deal with material condition safety factors? So maybe if we go back to this problem and we click on the partial factor tab, you will see actually there is the possibility of applying partial factors in a global sense to the material strength and also to masonry friction. If you wanted to if you wanted to apply a more localized set of material properties, you could do that as well. If you actually if I zoom in, suppose we had some, maybe I'll specify, I'll grab the whole of and a section of the pier. If we choose the contacts, we can see that we've got the default crushing strength of 5, but I could actually specify the overall crushing strength there as 2. Let's suppose if that was different masonry or deteriorated masonry, in which case that would have an influence on the. Did I actually implement that? Yeah, so that didn't actually have a great deal. Let's go down to 8 point. I misread that. I thought it said 0.945, but actually said 0.845. So actually, it's taken it down quite significantly. Okay, so let's see, is there any other questions? There's a question here. Where you have longitudinal fractures, you mentioned effective width should be limited to suit because you no longer have transverse distribution in the barrel, but the load will still be carried by the portion of outside the fractures. Therefore, isn't it overly conservative to limit the effective width? So I think you will have some distribution, arguably, through the fill onto that adjacent section of masonry, but you will have much less distribution than is indicated, for example, in typical assessment codes. So I guess it comes down to engineering judgment as to how conservative you want to be. Certainly, very often, we want to err on the conservative side, and then if we have the outcome is that the bridge has sufficient reserves of strength to carry whatever loading you want to apply, then you can be happy. If, on the other hand, you make a string of conservative assumptions and you end up condemning a bridge, then that's when you need to ask yourself, how realistic are those assumptions, and revisit assumptions such as this potentially. What I could say is that I've had experience of testing bridges in the laboratory which had, for example, a separation between the arch barrel and the spandrel walls, and certainly you did get some interaction between the fill and the spandrel walls, but it was at a reduced level compared with had they been fully attached. All right, just have a look and see if there's any final questions. I don't think there's any final questions, but I think we're out of time anyway, so I'll hand back over to Tom just to finish off the webinar. Thank you very much.
Thanks, Matthew, and thanks to everybody for attending today. So, as Matthew said, we're now near the end of the webinar, and we do hope you found it informative. As mentioned at the start, if it's prompted any questions that we haven't covered already, then please do get in touch with us, and you can do that either via telephone or by sending an email to info@LimitState.com, and we'll be more than happy to answer any questions for you. If you'd like to watch the webinar again, or if you think you might know somebody, colleague maybe, who would be interested to see it, then there'll be a recording available shortly on our YouTube channel, and we'll email you with a link once it's there. Lastly, please do also look out for the event notifications that we'll send out and post on our website for future events, future webinars, and that'll be on www.LimitState.com/events. And finally, just like to say thank you all again for listening, and we do hope you can join us again in the near future. Goodbye.